Welcome to Brain Vision.
Hi everyone, this is the solution to problem 34, chapter 24 of Cardinals Physics. Now this is a pretty involved problem to begin with. There's a lot of data that you're given, but it's going to all make sense as we go through the problem, so just bear with me. So first we're told that this magnetar is delivering an energy of 8.4 times 10 to the minus 6 joules of energy through electromagnetic radiation onto a telescope that has a surface of 75 meters squared. And the pulse, so the time in which this energy is delivered, is 0.24 seconds. So what we can do first is try and figure out what the power and what the intensity of this magnetar is. But the main thing that we want to find is the power, not the intensity. The reason is that once we know the power of this guy over here, we can use that power to find what the intensity is on the surface. And using the intensity on the surface, we can find what the size of the magnetic field on the surface is. So this is the agenda. So let's begin. So first we know that the energy delivered is going to be the intensity times the time that the light is shining, or the electromagnetic radiation is shining, times an area on which it shines, which for us is going to be the telescope, and the time is going to be the time of the pulse. So the energy delivered is going to be the power over the area of the sphere that is a distance d squared, 4 pi d squared, away from the magnetar. So the reason I have this 4 pi d squared over here is because the magnetar is shining its energy everywhere in space uniformly. So if we are a distance d away, then it's shining and distributing its power over a sphere of radius d. And so what I really have here is this is just P over an area where the area is the area of the sphere that has a radius of d. So it's distributing its energy over a sphere of surface area 4 pi d squared. So then I multiply this intensity by the time of the pulse and the area on which we are measuring the radiation, which is just the area of the telescope over here. So then I can rearrange this for P. So if we rearrange this for P, we get 4 times pi times d squared times E divided by TP multiplied on the bottom by the area of the telescope. Then this is equal to the power. So now we're going to use this formula for the power. And so we're going to try and determine what the intensity on the surface of the magnetar is. So let's go over here. And so we have that the surface on the intensity on the surface of the magnetar is going to be its power divided by an area, where the area is now the surface area of the magnetar itself. And so we're going to have, which is again assumed to be spherical, so it's going to have the area of a sphere, but this time of radius little r squared. And so since we want to find the RMS magnetic field, we know that this intensity can be set equal to C times B RMS squared divided by mu 0. And so now we just rearrange this for BRMS, and we get BRMS is equal to mu 0 times the power that we calculated before, divided by C times 4 pi little r squared, and all of this is square rooted. So now we're going to put in our value for P that we had found in the previous slide. Let me just fill in the details here. So now we have everything except for P. And so we're going to multiply this by the value of P, which we had worked out was 4 pi d squared E. So we have 4 pi d squared times the energy divided by TP, time of the pulse, times the area of the telescope. So I'm just going to divide this by TP times A of the telescope. And so we see that a lot of things cancel. So 4 pi's, well, not a lot of things. The 4 pi cancels. And so we have that this is equal to mu 0 times d squared times E, the energy, divided by C times r squared times TP, time of the pulse, times the area of the telescope, and it's all square rooted. And now you can see that here we're actually given every piece of the data that we need. So we have U0, AT, TP, R, D, E, and C. And so plugging in all the values, we find that the magnetic field is going to be pretty huge. It's 2.2 times 10 to the 6 Tesla. And so that is our answer.